Thanks a lot. So, yeah, after sorting out this little technical difficulties and finally getting a mic, and I hope everybody can hear me. All right. My name is actually Kai Kunze. I'm a PhD candidate from the Embedded Systems Lab at the University of Passau, supervised by Professor Paul Lukowitz. And in the next 40 to 50 minutes, we will, take a closer look at the state-of-the-art in wearable computing to get us started and give you a little bit a common background or common ground to start from some motivational slides. As I guess everybody of you knows, currently today we are in a state where computing is embedded more or less in all kinds of everyday devices. So your watch, your phone, your gaming console, car, washing machine, and so on. Although the I have already, so I'm fine.
Okay, but talk.
Okay. Basically, computing is embedded in everyday devices and everyday artifacts and objects, and we think that it should support us, in everyday life with our tasks, with our things we need to do. However, usually it looks more like this. This is actually in the background. There's an unstaged picture of my desk at the University of Passau, so of our office, and so basically. The devices we use today don't really support us in our everyday life. They more or less disturb us. And if we have this embedded technology, very close to us and near to us, so watch, mobile phone, and so on, the limiting factor no longer becomes, or the scarce resource no longer becomes actually processing power or memory, but user attention, so the attention of you. If the mobile phone rings, it disturbs your attention, it disturbs on what you were working on. And the vision of wearable computing, or also ubiquitous computing, pervasive computing, I tend to use them interchangeably. For me, they all kind of share the same vision. They come in different flavors. I know you can start religious wars about that, but in general, I forgot to switch on the demo. But in general, they all aim at supporting us with transparent computing, so computing we don't see, computing that is inherent, that is useful and unobtrusive as our clothes or similar. And how this is done is basically computing needs to perceive somehow the real world. So, all the chips and memory that is integrated in these everyday devices need the way to perceive us. And, how this is of course done now is using some kind of infrastructure sensors, microphone arrays, some fixed cameras, some other things, or body-worn sensors. So, in this case, for example, accelerometers or gyroscopes, and so on. And this actually brings me then also to a first demo, how this can look like. If you look at the top, you see the little a man actually moving, and what I have on my body is basically two little sensor nodes, one here and one here. It's a particle computer from the University of Karlsruhe, TECO, and what should happen is basically it recognizes if I'm waving over an accelerometer, and it should recognize if I'm sitting down. This is sometimes difficult. Difficult, please. No? Okay. Yeah, some problem with the live demo, but at least it recognizes the variance in the accelerometer. So basically, the processing is done on the chip. I'm even surprised that it currently works on this setup because I needed to use VMware and some weird other things to get it actually running on the laptop. But you see, actually, the nice thing is this was a demo implemented during a diploma thesis of Josef Neuburger. And he basically implemented all of this on the chip. So all the classification and so on is done on a small PIC chip, and I think around 64K of memory or so. So very limited device. Yeah, I thought at least I'd bring some kind of demo with me. Let me just stop the demo because I'm not sure later on it might get distracting. Okay, and continue with the presentation. Another way, another hybrid approach or also infrastructure sensor you probably already know is the Sputnik, which is also available here at the Chaos Communication Congress, the Open Beacon. Britta and Milos actually visited us at University Passau 2 years ago and also installed a system there, so we have also running a system of Sputnik in our lab. I just wanted to promote it because I really like the idea. They put out all of their layouts and all of the software in open source, and you can just basically download and profit from their experience as well. So basically now we have these sensing capabilities in our computing. So what do we want to support? Basically every high-level user activity that you can think of, and here's just some examples. So from everyday living, so you know these very mundane, very old examples of the intelligent fridge or the intelligent stove, the intelligent house, and so on, or healthcare, work and collaboration, so helping people not to endanger themselves, doing difficult tasks more or less, and of course also sport and lifestyle activities, so you know, as virtual trainers or similar. And this brings me now to a small outline of the view. So we started off with the motivation. Now we will jump into the application scenarios. I'll give some of more concrete examples there, and then we'll look at enabling technology. So you know, what do we usually use at the Embedded Systems Lab to build such demonstrators and such systems? And then I go into a bit more detail about actually my PhD work, opportunistic sensing. So I discuss some of the problems that current activity sensing or wearable computing systems actually have and some partial solutions. And in the end, we'll finish with some general issues. Here we will basically talk about two issues. One is how usable is the stuff? You know, it's maybe nice for researchers and for geeks, but is it really usable for the everyday person? And another issue I can't get around at the Chaos Communication Congress, of course, is privacy and privacy implications. So let's start off with a little video from one of our demonstrators. This is work done by David Banach, mostly as part of the Where IT at Work project. This is a huge integrated project.
Doctors with their work in...
It started, now I stopped it again, I guess. Ah, now it's working, okay. And this is basically a system that was designed to help a doctor doing his daily rounds. He strips on a Linux PC. This is a Belt PC from ETH Zurich, the Cubic. He wears on the one wrist an RFID scanner, on the other wrist a motion sensor, and sets up a Bluetooth headset. And basically with this, he starts his rounds in the morning and starting to visit patients. So, you know, he walks to the patient, basically scanning the RFID tag on the wrist of the patient, and with this he triggers an event in the system, and he basically gets all the information for the patient on the system, and then can use the motion sensor on his wrist, on his other wrist, to basically scroll up and down and select the corresponding report and check the status of the patient. And there's another gesture. Okay, now I think he'll show the scrolling. Yeah, right, so this is scrolling, this is selection. And there's another gesture to basically call for an MRI or so. He can just basically do this gesture and activate the Bluetooth headset. The context recognition part was implemented from our lab, so mostly David Banach. And this is actually not a mock-up. This was actually in place for 3 weeks in a hospital in Steyr, and with a fully working system. SAP was also, or is also a partner in the WIT project, and they actually did the backend. So basically, they did the interfacing to an R3 system. So we did a test run with real doctors, real patients with this technology. So, you know, it looks kind of maybe a little bit mundane, but if you think about it, we really pushed this out to doctors and got feedback from them. And so one of the first feedbacks we got is that, you know, this gesture recognition with the hand kind of sounds alright, but if you use this in a doctor-patient context and you use gestures, you know, scrolling up like this or scrolling down like this and then selecting, you run into some trouble depending on the cultural context of the people. So the next demonstrator actually used a capacitive sensor integrated in the jacket of the doctor, and you basically then he can basically scroll up and down by just moving his hand, and then selecting is then just a press and no longer side movement. There were 2 different flavors, a bigger one integrated over here and a smaller one down here. One of the requirements we got from the doctors was actually that they have their hands free, so they don't want to touch a stylus or they don't want to touch a mouse or something similar, because they might want to interact with the patient or do some search there. So this is one application scenario in healthcare. Another one, what we will look at, is an industrial scenario. This is some recording, some sensor recording for quality assurance, reenacted from ETH students at Zurich. From Skoda assembly line. So basically, you know, after a car is finished, what you have is usually a check if everything is all right at the end of the assembly line, this quality assurance step, and it's quite tiresome for the worker because he might forget something. You know, you have to, you know, check each door, you have to open each door 3 times and things like that, and check that the steering is all right, check the all kinds of moving parts of the car. And so the idea is later on to support this worker so he does not forget anything. And here you just see data recording, as I said, reenacted at ETH. We work closely together with them. This was basically, most of the work was done from Thomas Stiefmeier, student at ETH, and Georg Ogres, a colleague of mine. And here you see Clemens, another PhD student from ETH, actually performing these quality assurance tasks. And you see already that the setup is a little bit different. So you see more sensors. So you see these yellow bricks, they are motion sensors. There's the norm of the velocity and the acceleration from the hands, just plotted down here. And he was wearing force-sensitive resistors sleeves on each arm, so you get the muscle activity for each arm, and you see the raw data down here. And the only thing that is actually now classified in this video is the location. So we classify if he is on the right side of the car or on the front side. This is done with an ultra-wideband localization system, the 2 tags he wears on the shoulder. And as you already see, this looks very much different than this use case in the hospital, and this is more or less also how we do our data gathering, because sometimes if you want to recognize specific tasks, like now in this case, opening the truck or closing the trunk, you sometimes don't know which, and you see you have this repetitive task, so he has to push it down 3 times and so on. You don't know what to look for in the data, so you usually use you know, a more elaborate setup. My professor tends to call it Christmas tree setup, fitting to the season, because you put a lot of sensor on the test subject, and also usually use students as test subjects, so they cannot really complain at the beginning. So this is now I showed you kind of a regular or a more extensive work in industry, and now for the last application scenario, I want to take a look at more in sports and health.